welcome to our webinar on how to avoid HV failure with permanent PD monitoring. Back from that one. Yep. So, my name is Brad Monaghan and this is Thomas Whyte on my left-hand side. We're from EA Technology in Australia. At the moment, we're in Brisbane and we will start running through our presentation. Yes, good. So what we're going to run through today is condition monitoring and partial discharge. We'll do an overview of that and the benefits of monitoring. So that's 24/7 monitoring of the of high voltage assets. We've got a whole bunch of user cases as to why you would 24/7 monitor, with case studies all the way through there about how customers have used it to effectively monitor their boards and why they've done that. At the end, we will offer some one-on-one sessions. If anyone wants to book some sort of 15-minute time slots with Thomas or myself or anyone in the office, they can do so after this. We've got an email address to email and we can book them in. If anyone is keen to have a one-on-one chat about any questions they want answered or any way that we can help you out.
Just throughout the session, if you do have any questions, over on the right-hand side, there is a small questions tab. If you can send your questions as we go throughout the kind of webinar, that way we'll answer them either verbally to you or just through back to you via the questions box. Once the webinar is completed, we will be sending out an email with some supporting documents. And as part of that, we will have all the questions that have come in, as well as our answers to them. So if we do get a fair few through today and we don't have time to answer your specific question during the webinar, we will definitely be getting back to you afterwards.
All right, so let's get into it. So condition monitoring and partial discharge. So firstly, why do we condition assess our high voltage assets? At an operational level, we want to extend our maintenance intervals, prevent our failures and improve our safety. And then at an asset manager level, it's all about risk and money and time. So we want to look at determining the optimum replacement strategy for our assets. If they're getting old and their condition is getting worse, we want to figure out where we're going to spend that money and how we are going to plan over time for resources and procurement. What is partial discharge? So there's a little bit here, just an overview on partial discharge. We've covered this a lot in a lot of other webinars, but we'll do a quick run through now. So partial discharge is basically defects on the outside or on the inside of high voltage insulation that can't hold the volts in that's induced onto that defect. And you have sparks jumping across tiny little defects, tiny little gaps, and those sparks over time can build up and eat through high voltage insulation to the point where it can blow up your asset. It'll bridge out either phase to phase or phase to earth. It can cause a lot of chemical damage within inside the high voltage chambers, and it can be detected through various test techniques and various sensors. There's three main types of discharge. We've got internal void discharges, and that's where you've got defects on the inside of your high voltage insulation, such as gaps, splits, voids, impurities, anything like that. It can be caused from manufacture or from installation or degradation over time. Then we have surface discharges, and that's where you've got something wrong on the outside of the high voltage insulation. That's where you have you can either have impurities or sharp points or air gaps between the high voltage insulation and another asset, and you have electrical stress built up across that little air gap or along the outside of the surface, and you can have little sparks occurring there and little amounts of current flowing, and if you leave that there long enough, that can end up blowing up your asset. And we have corona. So corona is from a physical sharp point, and sparks are jumping from that sharp point into a gas, and that gas is usually air. And depending on where that corona source is, that can degrade your asset and eventually fail your asset. So how do we detect partial discharge and how do we detect sparks? So if we think about a spark, sparks will produce light because we can see a spark. It'll produce heat because the spark is a tiny little lightning bolt, and that will produce heat, and that heat can eventually cause damage to your insulation layers. Sparks will produce a smell because it'll produce a tiny amount of ozone gas every time a spark fires. if that ozone gas gets trapped inside a high voltage chamber, it can mix with moisture in the air, form nitrous oxides and nitric acids, and then start to eat away at everything in the chamber. So those top three things there, so light, heat and smell. We don't use any test equipment to find any of that stuff. Well, you can use a thermal camera to find heat, I suppose, but the thermal camera won't find every source of PD. It'll find low level stuff, or probably high level stuff, I should say, or stuff where you've got line of sight, which quite often with high voltage equipment you don't have. But the two things that we detect with our test equipment is sound and electromagnetic waves. So every time a spark fires, it will give off a lot of sound in the ultrasonic frequency range. If the sparks are loud enough, you can hear them with your own ears. And then something that we can't see but we can detect with electronics and different types of sensors is the electromagnetic waves. So every time a spark fires, it'll produce a pulse of electromagnetic energy that will flow away from itself. And we can detect that via our test equipment. Okay. So now let's start talking about 24/7 monitoring of assets. So back to PD, we can detect PD via offline testing, online testing. You can use handheld instruments, or you can use 24/7 monitoring. And so now we're going to start focusing on the monitoring. So this is, once your screen flips over, this is our high voltage Astute HV monitor. So what this will do is, this is a 24/7 monitor where you set the hardware up all around your switchboard or whatever it is you're trying to monitor, and put a whole bunch of sensors all around that switchboard. So we use different sensors such as TEV sensors, which is transient earth voltage sensors, and that will detect your internal void type defects. We put ultrasonic microphones and point those microphones into all different locations around your switchboard, and that will pick up your surface PD, it'll pick up your corona PD, and anywhere that there's sparks jumping a gap and those sparks are exposed to the air, that will give off sound that those microphones can hear. It'll also track temperature, it'll track humidity, it'll track the temperature of the pieces of metal that make up the switchboard if you put the correct sensor in the correct spot. And all of the sensors are continually measuring information. Each sensor gets its own data point. A lot of the sensors talk to each other. They have TEV time of flight between them, so we can figure out by analysis of the data where the PD signal is coming from. And all of that information goes back to a central processing hub, and then from there it gets stored on there, and it can go up to a cloud server where we can remotely log in and figure out what's going on. So there's no shutdown required to install this equipment. Everything's magnetic, so it sticks to the outside of the switchboard. You can also monitor your high voltage cables via RFCTs or HFCTs. So that's high frequency current transformers. What we do with them is we clip that around the earth screens of your high voltage cables, and we can monitor your cables as well as your switchboard via those sensors to figure out if PD is occurring. So with the one system, you would set it up at a switchboard, you monitor the switchboard itself, and you can measure the cables that are coming into the switchboard. We also offer a service at EA Technology that goes along with the monitor. Setting up the monitor is the first part of the process. You need to get the right sensors in the right location. You need to figure out what sort of PD activity, if any, is in your switchboard, and then focus those sensors to give you the best chance of finding it. From there, it's someone's job to look at the data, to monitor it over time and monitor the condition of your asset. And at EA Technology, we offer that service here. So the way it works is we would do continuous monitoring of the activity. The data gets started locally, and then it's uploaded to a cloud server. If a PD event occurs above a threshold, we set the threshold, we set the alarms, and alarm is then sent to us. We would then interrogate that data, figure out if it's what sort of PD it is, where it's most likely located, what it most likely is, and then we figure out what the customer should, the best course of action for the asset owner to take in that instance. And then we would then inform that customer of what's going on. While during those conversations, we keep an eye on the activity. We give advice to the customers about what they should do, what signals they've found, Usually what we do is we'll get people to remotely analyse if any high voltage switching happened or anything happened at the substation that could cause these PD signals to come through. They might have had a load change, there might be big temperature changes, there might be people getting into the switchboard and doing things. And we can help out with, analysis of what it most likely is. Usually also we'll ask one of the customers to go down to site and do a handheld survey to figure out if they can focus more closely on where the PD signals are coming from. And then we manage everything during the whole event, and then we always give reports on what's going on. And then we continually monitor everything else over time and see how everything's performing. So this is what the system looks like when it's set up on switchboards. You can see a whole bunch of TEV sensors and ultrasonic sensors listening into your switchboard. Now, the benefits of monitoring. Why would you monitor? Monitoring can capture a much shorter point of where you can detect a failure to when it actually fails, as opposed to handheld testing. So if you were going around to your switchboards and doing handheld tests, you might do them every 6 months, 1 year, 2 years, 5 years, depends on what your maintenance schedule is for performing a PD survey. We know that there's PD sources out there, or failure modes that are out there, that can go from absolutely no PD activity at all to come up to a level where it can be detected, and then it can short, and then it can short out and cause a high voltage failure in a relatively small amount of time. It can be a matter of months, or it can be a matter of weeks, or it can be longer than that, but it depends on the defect itself, how much energy is in the defect, how much distance you have worth of high voltage insulation left before your sparks are going to fully bridge out the gap. So if you've got a 24/7 monitor there, you'll be able to pick up when something's occurred straight away, and you'll know that something's happening straight away. You can start to plan your actions as soon as you find it, rather than trying to rely on an annual PD survey of someone picking up a fault. So the monitor will, because it monitors environmental conditions over time, we can see if things are how they trend with temperature and humidity. We can see how they trend with load changes, and basically all that sort of stuff is self-explanatory in terms of that. But here's a picture of the P2F curve. So there's always a point at which a failure starts to build up, and then there's a point at which the defect can be detected. That might happen at the exact same time, or the signals might be so low that it might take a little while before a sensor can actually pick up that there's something wrong. And then there's a certain amount of time before the asset will actually fail. So understanding the consequences of failure of the assets will let us determine the most cost-effective way to apply PD testing. If we've got low consequence assets, so assets that are fairly cheap, that you're not so worried about in terms of risk, in terms of safety, in terms of financial or production, you might want to put in a periodic interval of testing of, say, every 2 years or annually or something like that. But then when you get medium consequence assets or high consequence assets, so they're your main switchboards, they're the ones that you can't afford to have failure inside, because you're going to get penalised with minutes off supply penalties or production penalties. You may want to bring that down to test it every 6 months or annually for a handheld test. And then the more critical it is, you might want to do it every 1 to 3 months, or consider doing your permanent monitoring to keep a very close eye on it. Okay, so let's get into some user cases for 24/7 monitoring. So this is, it's not limited to this list, but this is a pretty comprehensive list of why customers and high voltage asset owners use 24/7 monitoring. So it's going to increase the chance of preventing failures. If you can detect a failure, you can do something about it before it fails. There's safety mitigation, risk mitigation, they're two of the big ones. You've got people working inside these substations. You've also got the general public that might be near the substations. Another reason is unknown condition data. So sometimes there'll be a switchboard where the asset owner doesn't know exactly if there's a problem inside the switchboard, or they don't know how to detect a problem if there is a problem. and so they may not have much condition data on that asset. And we know that one of the biggest causes of high voltage failures is your high voltage insulation breaking down through partial discharge activity. So detecting PD is a very good thing to do to stop a failure. You may want to prolong the life of an asset. So you may have an asset, a switchboard that's due for replacement at a certain point in time because of its age mainly. There may be other factors that go into figuring out when you're going to replace the asset. But what you can do is put a monitor on it and prolong the life of that asset. We've had customers that have been able to extend the life of switchboards by 2, 3, 4, 5, even longer years because the monitor's on there. We're not detecting any PD, and they're happy to live with the asset because the risk of failure is low at that point. You might want to monitor known asset failure modes. So you may have a certain type of switchboard that has certain types of defects in it that fail. So around the world, you know of switchboards that have blown up because of a certain type of, a certain type of CT or a VT or a certain type of connection or a bus connection that fails. You can't find any problems in your switchboard, but you don't really know if it's going to fail or not. So monitoring that switchboard is a good idea. You may want to trend known PD sources. So you might have a switchboard where you know there's PD inside it. You can't do much about that PD, but in terms of replacement, because you don't have the money to replace it or the time to replacement, or you don't know if you need to replace it because the PD levels aren't really all that high. So what you can do is trend how those PD sources are performing and look for an upward trend. If they start to trend upwards, that's the time to execute your plan of turning it off and swapping out, replacing things at that point in time. Monitoring after a failure is a good idea. So if you have an explosion in a switchboard, that explosion can cause secondary damage throughout the other chambers. It can blow carbon and source up the chambers. It can mechanically move things. And what is a good idea is to monitor that switchboard for a certain amount of time afterwards to see if there's any secondary failures. And the last one is deferring maintenance. So if you are due to do maintenance on something and you just cannot switch it out for whatever reason, you can justify putting the maintenance off if you monitor it for any failure modes. As long as you have no inkling that there's anything else wrong with it, monitoring is a good idea. So I'll hand over to Thomas now, who will go through some of these use cases.
Thank you. Perfect. So Brad's gone through a bit more of the technical side of the monitoring and everything like that. But what I would like to go through today is less on the technical and the physical analysis of the monitoring, but on how we have worked with our clients to achieve some of their goals and prevent failures using these different user cases. And the reality is all condition monitoring really does just come down to asset management and risk management. So it's all about which of these cases best apply in your network. And the reality is it's normally multiple of them. And a lot of the case studies I'm going to go through here can apply to multiple different user cases, but it's just we're trying to go through and take it out to see how this can be applied in multiple different ways. Because like most testing, and especially with 24/7 monitoring, how you apply this testing to your assets and to your networks is so crucial in the data and the results that you get out coming from. So Brad did touch on testing intervals quite a bit, but here is just an example of how things can run away quite quickly. So what we've got here is a cable termination in an airfield cable box, and we'd been monitoring this site for a number of months before we saw anything. And we were monitoring it because we know there were other problems on the switchgear, but this particular cable box was being monitored because we have, in previous experience, seen problems on them. And suddenly we saw a quite sudden rise in ultrasonic activity. It wasn't incredibly high level, but it was enough to trigger all of our alarms. But this rise in activity happened, if you look at the pot and the bottom, in under a day. It was quite sudden, from absolutely nothing to not high level PD, but something was definitely not right inside that cable box. Luckily, due to the alarms, we were able to call our client and they were notified. We looked into it. We did an on-site investigation with the UltraTev +2, And we were able to come to the conclusion of, yes, the PD source had emerged from something that was previously not there, but it was low enough levels that we were willing to monitor the levels and plan an outage as soon as possible. So the best thing about this is that the client was able to be informed and do planned maintenance rather than this coming up and them not knowing about it. Traditionally for them, it would have been up to a year because they do yearly PD surveys if they aren't monitoring the board. This really does show that something can pop up, and if you can get to it, early intervention is normally an earlier fix. If you look at the picture in the bottom right, you can see this was purely caused by phases that were too close together. So because we found this problem quite early, it was just a matter of doing a bit of a cleanup on the different phases, putting a bit more separation between the phases, and then putting it back in service. However, if this had have been worst case scenario, there was no monitoring, and it took a full year between when the PD source first started to initiate and when they did that yearly survey to find this defect, that damage could have been a lot more severe, and it wouldn't have been an easy fix like it was for them. What we have is that exact process in a lot more detail with this case study. This is one where we've been monitoring this board for a very long time, and what there was initially was a pitch-filled cable box leading out to a transformer. This pitch-filled cable box had high-level TEV signals in it that, again, we were monitoring, and eventually the client was able to do the maintenance on their board. And when they did it, they melted out that pitch and they replaced it with a G38A compound, which is a substitute for the pitch because they didn't want to put the pitch back into that cable box. We decided that after the maintenance work was done, it would be best to continue to monitor this particular panel to make sure that everything was good. And what we actually found over the course of the next 4 months, this PD source, or a new PD source, began to emerge. And luckily, because we were monitoring this in real time, we are actually able to show you a video of this fully developing, and I'll put that up in a second. So what I am about to show you is a video of a PD source forming in that new compound filled cable box. So this is a phase plot, and you'll be able to see it developing over a 2-month period. So I'll just play this now, and I'll come back to you once we have seen it. Yeah, it should work. So far. So hopefully that video did play quite well for all of you. If it was a little bit choppy or buffery, we are going to be posting that to our LinkedIn over the next week or so you can have a really quite good look at it. But what that video showed was basically a PD source developing from nothing to up to about 30 dB, which is medium to high level, and it was quite interesting to see it form because you could see it was actually multiple different voids and PD sources all within the same phase, and we could watch it grow. That particular source there in the video was 2 months worth. We've kept trending that for about 4 or 5 months now, and it has continued to change, and we will be looking to do a longer case study on this in the future. But all of that data that you can see there, we can see live for these videos, and it shows you just how quickly these can come up out of nowhere. And what I'd like you to start thinking about is if you do PD surveying using the handheld devices, what is your test interval? And if that type of source did start to emerge on one of your assets, what are the chances that you would be getting to it within the 3 months that that video, or the 2 months that that video showed? And how quickly can you react to those types of problems? And that all relates back to the PDF curve, which Brad was talking about. And it's what level of risk you are willing to run with your yearly testing on any condition monitoring project. Just a quick back. And it also does feed in quite closely to safety and risk mitigation. So everyone likes their workers and the people in the room to be as safe as possible. So these monitoring systems, we work with multiple clients to put 24/7 monitoring in for purely safety and risk mitigation. There's not necessarily PD sources on some of the boards we monitor, but some of them are purely there to make workers safer in that environment. One of the key ones is we monitor a board that has restricted access. It's old, it's had a lot of known failures in the past, and they are looking at replacing it. But until they can replace it, before anyone can enter that room, they want to verify there is nothing going on, and PD was the way that they verified that. Previously, they used to have a person enter the room and they used to do a PD survey by hand before carrying out any other types of work. But of course, that still requires someone to enter the room which they've deemed dangerous. So what they did was they installed a 24/7 monitor and they installed alarms. So all of that work can be done before a person enters the switch room. We had a very similar project where we had a switchboard and it had no PD on it. We've done the initial surveys, but they had a long-going project of they were upgrading the protection circuits for that substation. At the time, the protection boards were located in the same room as the switchboard, and also workers were working long hours in the same room as the HV switchboard. So a 24/7 monitor was installed, and again with alarms and quite quick response time to make it so the people who are working in that room can be assured that if anything is going on, there will be a quick response to it. And that's something that the company has done to reduce their risks as a company and reduce the risk for their workers. We've also had multiple circumstances where clients have just not particularly known much about their switchgear. And 24/7 condition monitoring is really good for that. So when you do your handheld tests, you're getting a snapshot in time of what is happening at that exact moment and what is going on. Why 24/7 monitoring is so much better for getting good quality condition data is you will see what is going on that board over your full array of network operations. You'll see it at high load, low load, different environmental conditions, and everything that you can do, you will get a sample of compared to just a single snapshot in time. One of the ones that I did quite recently was actually a board that was a little bit over 20 years old. There'd never been any significant problems on this board, but they were starting to get a little bit worried about it and they just wanted to know what was happening. So we did a short 3-month project where we were going to install a PD monitor on it so we could see what happened throughout their entire network operations. When we went to site, we did a handheld survey and there was no PD sources at all. However, due to the nature of their network, multiple of the panels were de-energized, and they kind of switch load between panels to operate different bits of machinery. What we noticed is 2 days after we installed the monitor, one of the de-energized panels was energized and load was transferred, and a medium level PD source did appear. From that, we were able to trigger the alarms which we'd set, and we were able to go to the client and investigate within 24 hours. And on the right picture there, you can see the panel, and that's what I opened up with the client. And there was no immediate and obvious damage. It wasn't a really high level PD source, but once we started to look into it further, this is what we started to see. So on the top there, you can see one of our analysis plots, and you can see the yellow and green lines, which were the sensors monitoring this particular cable box. So immediately when they did swap the load over to that panel, an ultrasonic PD source started. We were able to call the client, and I actually went there personally. We did a handheld test to confirm exactly what part of the chamber it was coming from, and then we were able to de-energize it for further investigation. What we found after we had a good look is the bus bar didn't have enough clearance when it went through one of their CTs. You can see that in the bottom left picture there, it's just far too close. Then you can see all the degradation of that CT, and there was even enough energy there for it to be eating into the metalwork and that bus bar, and you can see a bit of black pitting into the metal in that bottom right-hand picture. So before this, with all the engineers we talked to from that company, we were all quite confident that the board was in really good condition. And if I had have just gone to site that day, done the regular handhold test with those panels de-energized, we likely would never have seen this problem. Whilst this problem wasn't detrimental, I don't believe it was going to fail tomorrow or within the next week. It was purely come down to a game of luck that if with a handheld survey, you would have been there at the right time to detect this problem. And it could have gone a number of years without being detected if we hadn't have done this monitoring system. And this was a great find. Me and Brad actually have this CT sitting on our desks in the other room in our office. What we've also worked quite well with customers on, and it comes down to, again, better quality condition data lets you make better quality decisions about your gear. One thing is a lot of electrical assets are starting to age, and a lot of them are approaching end of life, particularly in DNOs, and they've been around for a while. So what we work with is using this high quality condition data across all of the different network conditions to extend the life of switchgear. A particular example we have of this is we had a company who was set to replace one of their switchboards in 2020. Due to construction projects and quite big ones nearby, they relied on a direct feed from the substation in order to finish the project. As that construction project ran longer, it was basically necessary for them to push out the end life of that board and push out its replacement until the construction project was also finished. So this required a huge amount of risk analysis. What do we need to do once we start to push the life of an asset out? And that kind of feeds in all to things like your AIM and your CBRM and your asset management program. So what was decided is that they would put 24/7 monitoring in. We would be quite strict with it, and we would look at everything and we would give them the data. And once again, we were able to analyze it in real time, give them quick things, quick updates on what is going on with their board. What it also allows them to do is target their maintenance, which we'll talk to a bit more in detail in a second. But this way they can look at what they've got, look at what problems are arising, because with a known replacement of that board coming, you don't want to be doing a huge amount of unnecessary maintenance. You want to be able to target and do what you need to do to get it through to end of life. Something other we work on with our clients is known asset failure modes. So everyone has assets on their network that have experienced failures in the past or worldwide have experienced failures. It can be due to installation defects that are common in your network. It can be due to manufacturing defects of specific types. So we do have a client who experienced a couple of failures on their 11 kV current transformers in a very particular type of board. They did an investigation and they did find that it was due to a manufacturing defect. So when that does happen and it's due to a manufacturing defect, you have to start to assess where else in your network could this problem be arising. Unfortunately for them, they did that analysis and they found that they had these exact same CTs installed in multiple other boards. And they weren't particularly sure, because they were a manufacturing defect, how long they have until it does go to failure, because they'd been installed for quite a long time. So what they decided to do was get a single 24/7 monitoring kit that they could move around all of their different substations. And they started to do a roving monitoring system of short term on a 3-month basis. And that allowed them to cover their entire fleet of assets at a significantly smaller cost while still getting good high quality data that they could use to navigate their way through this problem which had led to failure previously. And that's something that can be really helpful when you are managing a larger fleet of assets. Permanent monitoring doesn't necessarily have to be permanent. It can be both, or 24/7 monitoring doesn't have to be permanent. It can be both short-term and long-term. It can be tailored to fit what is necessary for your network requirements. And here is another good example. This is an example of an asset that we knew the specific type leads to failure, but more of an asset type which, through experience, we've learnt tends to have problems, and that is rackable VTs, especially these cast resin ones. What Brad and I have found through our monitoring and our PD surveying over the years is rackable VTs do have a number of problems which can lead to both mechanical failure and PD. This particular one, we believe, was wrapped in on a slightly wrong angle, you'd say, and there was mechanical force pushing it, which eventually led to the cracking you can see and the large amount of electrical charring you can see in that top right picture. So when we initially started to monitor this board, it was probably 2 or 3 years before this particular failure happened. And the reason we monitored this VT so specifically is due to our experience in the past and knowing that these issues can crop up out of nowhere. And that is exactly what happened with this VT. Over the previous 2-3 years, we'd had no indication at all that any PD was likely to form until one day it just cracked. No prior signs, but it triggered our alarms. We were able to notify the client and they were able to do planned maintenance. And it was quite a big win because if you can, seeing that picture there on the right, that is not something you would like to remain in your network. What we do often, and the reason actually that particular example was on the switchboard in the first place, is monitoring known PD sources. A lot of the people here and a lot of people do already do +2 and PD surveys yearly, and you do find problems. The issue is not all things either require immediate attention or you're not able to give them immediate attention. So sometimes it is more practical to install this 24/7 monitoring to keep a really close eye on these problems until you can get that planned outage or you can get the spare parts in. The particular example there was a pitch-filled cable box, and it's one we've talked about a lot in the past, but it was incredibly highly loaded and they were having difficulty switching the load. So we kept the monitor on it until they could get the shutdown organised and do the work that needed to be done. But when you are doing your yearly handheld surveys and covering a large amount of assets, when you do find problems that you aren't quite sure what to do about, or you do need a while to plan the works or get the parts, monitoring is a really good alternative to keep that asset online until those works can be done. And sometimes even after the works are done, as we've talked about, you can have more issues crop up. Monitoring after failure is a quite important one. In an ideal world, none of us would have HV failures, none of us would have asset failures, but it does crop up from time to time. And the effects of this can be devastating, not only for that asset, but the assets around it. Dust and soot and arcing is thrown everywhere, and it can be quite detrimental to everything around it. So when you do the maintenance to get these assets back in service, it's really important to keep a close eye on them, because you can have issues tend to crop up down the line on the surrounding assets, not just the one that failed. And a really good example of this is what we found in our private network. And what they had was a snake, true to Queensland, bridged out their 33 kV overhead bus in their switchyard. And we work quite closely with this company, and we do 3-month surveys. We go and we cover all of their different assets. And for one particular one, we found that it gets fed directly from this yard. And after this event, we found that a PD source had occurred from nothing, something that was previously perfectly fine. We now had an internal void type problem in that in an 11K current transformer. So when you do have these network events or failures, there are kind of cascading effects that can affect other assets throughout your network. This particular one we weren't monitoring at the time, but they did decide to install monitoring on this asset to make sure that it wasn't snowballing. It is quite interesting because 3 months is very frequent to be doing handheld surveys. So even that, we've seen it has grown quite a lot. If we were doing yearly surveys and things, this may have escalated a lot further. But luckily we were able to monitor it. There was very little change as it led through a couple of months until they could get the parts and do the replacement works. But it just shows what can happen when you do have that sudden shock to your network. It can create problems in places you weren't expecting. Deferring maintenance is something I've talked about a bit already, but the more you know about your assets, the more that you can do planned and targeted maintenance to make the right decisions. So this particular deferral of maintenance, it can be due to a couple of reasons. And a couple of our clients have very high load on certain switchboards with no redundancy. Even if they wanted to switch off it, they can't without completely de-energizing large sections of their network. We've also had issues with clients with incredibly long lead times on parts, and that was really exacerbated during the COVID-19 pandemic with wait times on particular parts going up to like 18 months we've seen. You also have critical feeds, which you just can't turn off for whatever reason your network does, but what crops up a lot is high value production feeds, and that's in a lot of manufacturing and mining sector, and where you just can't afford to have these parts of your network off. So the more data you can know about these particular sections of your network, the longer you can justify pushing it back. One example we have is we had a board which they were doing yearly surveys and they found very high level PD. Through a bit of investigation, we actually found it was the TEV signals were originating from the VT fuses, and it's a picture of them there on the right. And this particular signals were coming from that. We deemed them not to be too high of risk just due to the nature of the VT fuses, but they needed one of them back in. So the client did decide they would pick the best fuses they could get, put them back into service because it was critical for protection and metering. From there, we do have monitoring on that board permanently, and we can trend to know if this PD is going up or down, and they can make informed decisions on their board. And so far, they've been able to really well manage that system, and there haven't been any further issues arising once they've done some of the replacement works. I'll hand back to Brad to do a bit of a summary for us.
Cool. Thanks, Thomas. Yeah, so just in summary, we've got a significant proportion of HV equipment failures is attributed to PD. So when PD is going to break down your high voltage insulation over time, and that's going to lead, or can lead to high voltage failures. 24/7 monitoring is an effective way of preempting HV failure. And it can be used for short and long term. As Thomas said, you can move these systems around to map certain switchboards over certain periods of time, or for certain reasons at certain periods of time. Now, we do have a questions tab that you guys can write any questions into,
yep,
and we can answer them.
Yep. But whilst we do get some to come through,
yep,
we are doing private kind of 15-minute one-to-one sessions if you would like any more information from Brad, myself, or anyone in the team. If you do want to email, there's an email at the bottom, and you can book one of those sessions. It doesn't necessarily have to be to do with this webinar monitoring in general. If there's just anything you would like to discuss with us, like a little bit more information on, please feel free to book one of the sessions and you can have a good chat with us about that, just anything you particularly want to know. If you do have any questions now that you'd like us to answer, feel free for them to come through. We'll give it a couple of minutes. Other than that, you will be receiving a video of this entire presentation come through via email, as well as a summary of all of the questions we do get. You'll get some information, especially on the question and answer sessions we are planning on running next week, I believe they are, as well as if you do follow us on LinkedIn, you will see things like that PD development video coming up and a couple of other case studies which we post on a pretty regular basis. We do have suspiciously no questions. Well, in that case, we might call it there.
Yeah, you might call it there.
Thank you everyone for tuning in. Hopefully you did find it helpful. If you do need anything, feel free to contact to either Brad or I, and we'll get back to you with anything you need.
All right.
Thank you very much.
Thanks everyone for joining in.